If you've ever seasoned a steak, cured a piece of meat, or simply sprinkled a pinch of table salt on a garden slug, you've witnessed one of the most powerful physical processes in nature. Salt is the ultimate dehydrator. It is a biological sponge. It doesn't just sit on food, it actively rips the moisture out of cells, drying them out, rupturing their walls, and destroying the bacteria that would otherwise cause decay. It is so hostile to living cells that for thousands of years, humans used it as our primary weapon to preserve food and keep pathogens at bay. And it doesn't just apply to microscopic bacteria. Imagine you are stranded in the middle of the ocean on a life raft. You are surrounded by millions of gallons of water, yet you are dying of thirst. If you give in to temptation and drink that ocean water, you will accelerate your own death. Your kidneys will be forced to use more fresh water to flush out that salt than the amount of seawater you actually drank. You would literally dry out from the inside, your organs shutting down one by one, surrounded by a world of water. Even if you take a freshwater fish, like a goldfish from a pet store or a trout from a mountain stream, and place it into the ocean, the result is tragic and immediate. Within hours, the salt water will draw the moisture straight out of its body. Its cells will shrivel, its blood will thicken, its tissues will bleed, and it will die of extreme dehydration. Yet right beneath the surface of that very same ocean, billions of marine fish are swimming, hunting, and living their lives. They are literally marinating in this toxic, dehydrating soup 24 hours a day, 7 days a week. They don't shrivel up, their tissues don't dry out. So what is going on? How do ocean fish survive in an environment that is actively trying to suck the life out of them every single second? The answer isn't a single simple trick. Just like the premise of our previous story about scavengers and rotten meat, the idea that salt can't kill sea fish is actually slightly misleading. Salt can and does kill sea fish. If an ocean fish gets injured, if its protective slime coat is scraped off, or if it falls ill and its metabolic energy drops, the ocean will immediately take advantage. The salt will invade its body, flood its cells, and dehydrate it to death. The reason we don't think about this is simple. We only see the healthy swimming survivors. We don't see the millions of fish that weaken, lose their chemical balance, and sink to the ocean floor to be eaten by crabs and microbes. When you watch a tuna cut through the water like a silver bullet, or a clownfish darting around an anemone, you are not looking at an animal that is magically unaffected by salt. You are looking at a survivor. You are looking at an animal that is locked in a relentless, exhausting, high-stakes chemical battle. They aren't immune to the dehydrating power of salt. They are actively, aggressively fighting it every millisecond of their lives. To survive in the ocean, a marine fish must run a highly complex, energetic desalination plant inside its own body. And to understand how they do it, we first have to look at the invisible physical force they are constantly fighting, a law of nature called osmosis. To understand the fish's dilemma, we have to look at how water behaves. In the physical world, water is a diplomat. It always wants to balance things out. If you have two pools of water separated by a semi-permeable membrane, a barrier that lets water pass through but keeps larger molecules like salt trapped, water will naturally flow from the side with less salt to the side with more salt. It does this to dilute the saltier side, trying to make the concentrations equal on both sides. This movement of water is called osmosis. Now let's look at the numbers. The ocean is incredibly salty. Typical seawater has a salinity of about 3.5%, which translates to an osmotic pressure of around 1,000 milliosmoles per kilogram. The body fluids of a bony marine fish, its blood, its cellular fluids, its tissues, only have a salinity of about 1%. That's roughly 300 to 400 milliosmoles per kilogram. This means the ocean is roughly 3 times saltier than the inside of the fish.
Because of the law of osmosis, the water inside the fish's body desperately wants to escape into the ocean to balance things out, and it has an incredibly easy way to leave. While a fish's skin is relatively thick and covered in a protective layer of mucus that helps block water loss, its gills are a completely different story. Gills must be incredibly thin, delicate, and highly permeable to allow oxygen from the water to diffuse into the fish's blood. But because the gills are so thin and constantly exposed to seawater, they are also a massive open exit door for water. As a result, a saltwater fish is constantly losing water through its gills and skin. The ocean is literally dehydrating them, pulling the fresh water right out of their bloodstream into the vast sea. If they do nothing, they will shrivel up like raisins in a matter of hours. So how do they replace that lost water? They use a strategy that sounds completely counterintuitive, almost suicidal. The first active line of defense for a marine fish is to drink. If you look at freshwater fish, they almost never drink water. Because their bodies are saltier than the fresh water they live in, water is constantly rushing into their bodies via osmosis. They are practically drowning from the inside out, so their challenge is to pee out excess water constantly. But marine fish have the exact opposite problem. They are constantly losing water, so to stay hydrated, they must drink seawater, and they drink a lot of it. A typical marine bony fish will drink anywhere from 10% to 30% of its total body weight in seawater every day. For a human, that would be like drinking 20 liters of salty, brackish ocean water a day. But this presents a massive biochemical crisis. Drinking seawater puts a high concentration of toxic salt directly into their digestive systems. So how does the fish's digestive tract handle this? As the seawater enters the fish's esophagus and moves into its stomach and intestines, the gut lining goes to work. The cells lining the intestines actively pump sodium and chloride ions out of the swallowed water and drag them directly into the fish's bloodstream. By pulling the salt out of the digestive tract and putting it into the blood, the fish creates a temporary local osmotic gradient. Because the blood around the gut is now saltier, the water left in the intestine finally follows, absorbing into the blood vessels. This is a brilliant physical hack. The fish has successfully absorbed the water it desperately needed to stay hydrated.
But it has paid a terrible price. By absorbing all that salt to get the water, the fish's blood is now heavily overloaded with lethal concentrations of sodium and chloride. If that salt stays in the blood, it will cause cellular collapse, heart failure, and death. This brings us to the most critical high-energy layer of the system, the cleanup crew. If the gut is where the fish takes in the salty poison, the gills are where the poison is aggressively thrown back out. When we think of gills, we think of lungs. We think of oxygen and carbon dioxide exchange. But in marine fish, the gills are also a massive, high-powered industrial desalination plant. Embedded in the delicate, feather-like tissue of the gills are specialized cells called chloride cells, also known as mitochondria-rich cells. These cells are absolute wonders of evolutionary engineering. As their name suggests, they are packed with mitochondria, the powerhouses of the cell, and they need every single ounce of energy those mitochondria can generate because they are performing a biochemical feat that defies the natural flow of physics. In normal physics, substances diffuse from areas of high concentration to areas of low concentration. But these chloride cells are doing the exact opposite. They are grabbing sodium and chloride ions from the fish's blood and forcefully pumping them out into the ocean, even though the ocean is already 3 times saltier than the blood. This is what biologists call active transport, and it requires immense amounts of metabolic energy in the form of ATP. Inside the membrane of each chloride cell, specialized molecular motors spin and cycle tirelessly. They bind to the excess sodium and chloride ions floating in the blood, lock them in, use energy as fuel, and physically push those ions out across the gill membrane, releasing them into the sea.
It is a violent, non-stop microscopic bailing process. It is like trying to bucket water out of a leaking canoe, except the water level outside the boat is higher than the boat itself. You have to throw the water out with immense force just to keep from sinking. Because of this constant molecular labor, marine fish spend a massive portion of their daily oxygen and food energy, sometimes up to 15% of their entire metabolic budget, just to run these gill pumps. They are literally paying a salt tax on every single breath they take. While the gills handle the vast majority of the sodium and chloride, seawater contains other dangerous salts. It is filled with calcium, magnesium, and sulfate. These heavier ions cannot be easily pumped out by the gills. This is where the fish's kidneys step in. In humans and other land animals, our kidneys are designed to filter waste by dissolving it in large amounts of water and flushing it out of the body. If we have too much salt, our kidneys use up our precious internal reserves to pee it out. But a marine fish cannot afford to lose a single drop of water. If its kidneys work like ours, the fish would dehydrate itself just trying to urinate. So the marine fish's kidney has evolved to be highly specialized. In many marine species, their kidneys have actually lost the structures that filter out large volumes of water. Instead, their kidneys act as highly targeted ion filtration systems. The kidney actively grabs the magnesium, calcium, and sulfate from the blood and packs them into a tiny, highly concentrated, paste-like trickle of urine. By producing only a minuscule amount of highly concentrated urine, the fish manages to throw away the toxic heavy salts while hoarding and recycling every precious molecule of fresh water within its body. This entire system is highly specialized, and it explains why the barriers between freshwater and saltwater are usually so absolute. If you put a freshwater fish in saltwater, it lacks the high-density chloride cells in its gills to pump the salt out. It cannot drink seawater safely, and its kidneys are built to dump water, not save it. It shrivels and dies. But there are some evolutionary rule breakers. Consider aeroline species like salmon, barramundi, or bull sharks. These animals can travel between freshwater rivers and the open ocean with impunity. How do they do it? When a salmon prepares to migrate from the fresh river where it was born to the salty depths of the ocean, its body undergoes a radical hormonal transformation. Over the course of days or weeks in brackish estuaries, it literally dismantles its freshwater cellular machinery. It remodels its gills, building millions of marine-style chloride cells from scratch. It triggers its behavioral drive to start drinking water. It alters its kidney function to conserve water rather than flush it. It is the biological equivalent of a vehicle converting itself from a submarine into a spaceship mid-voyage. So why can't humans do any of this? Why did we lose this incredible chemical flexibility? The honest answer is evolutionary trade-offs. Millions of years ago, our ancestors left the oceans entirely. We adapted to terrestrial life. We traded wet, highly permeable gills for dry, protective skin that locks moisture inside our bodies. We developed internal lungs that protect our breathing surfaces from drying out in the open air. Because we no longer had to fight a constant osmotic battle against a surrounding ocean, we could redirect that massive metabolic energy towards building larger brains, warm-blooded metabolisms, and complex muscular systems. We optimized for land, and that optimization became permanent. We didn't lose the ability to drink seawater because we got weak. We traded the energy-intensive machinery of the gill pumps for a highly efficient land-based lifestyle. So, the next time you look at a marine fish gliding effortlessly through the ocean, or the next time you season your food with a pinch of salt, remember what's actually happening beneath the waves. The salt hits the fish from all sides, a constant physical force trying to pull the water from its cells. To fight back, the fish drinks the very salt water that would kill us. Its gut absorbs the water, pushing the toxic salt into its bloodstream. But before that salt can do any damage, it's grabbed by billions of tiny, high-energy chloride cells in the gills. Powered by a biological firestorm, these cells pump the salt back out into the ocean, fighting against physics every single second. Meanwhile, highly specialized kidneys filter out the remaining heavy ions, squeezing out waste while hoarding every precious molecule of fresh water within its body. It is not a single defense. It's a multi-layered, active biological fortress refined over millions of years of evolutionary warfare. Marine fish aren't just swimming in salt water. They're actively, brilliantly, and heroically conquering it. And that vast, hostile, dehydrating ocean, from their perspective, it's just another day at the office.